Welcome everyone, and welcome to the first lecture of this course. And we will be talking about uncontrolled diode rectifier circuits and understanding their operation. So if we see the total course structure and the content, we can see that we are basically starting with the first topic under module A. So we have divided the course into 4 modules, which you can see, and in the first module basically we are going to cover the traditional diode and thyristor based rectifiers, both single phase and 3-phase, and we'll start with the diode rectifiers today. Most of this course content, as what we are going to cover, is basically covered in all, like first course on power electronics. Typically in India, this is at the undergraduate level, and we covered it in details. So we will kind of like go through it once more so as to get a feel of what we are going to look into the further into the course. And also we will try to give you some additional details here and there which can be useful. These are the reference books which can be useful for the diode bridge rectifiers, but I will also recommend that you go through the application notes from different manufacturers like Semicron, Infineon, Mitsubishi, etc. Because these application notes from different manufacturers, these are a very good source of information, and whoever is going to design, suppose, a rectifier based on power devices, they must consult these application notes apart from papers and books. So let us first see what are rectifiers and why do we use them. Okay, now here rectifiers, there are different types of rectifiers, but we use basically rectifiers to convert AC to DC. Okay, so we have an input to the rectifier as AC quantity, AC voltage typically, and we convert it into DC voltage. Okay, so this is used extensively. Rectifiers were very popular in DC motor drives. Okay, and one of the biggest application always was different types of DC motor drives, say used in traction motors, in trams, in various process industries. But as you can understand, DC motors are not so popular nowadays. As of 2025, DC motors are no longer popular so much, and AC motors have completely kind of like replaced DC motors. So the use of rectifiers for DC motor drives is no longer the prime objective, or not so popular nowadays. So, but diode rectifiers are still quite popular. Diode rectifiers are used in AC drives also. For example, if you see induction motor drives which are, say, used in, say, pump applications, for example, they will take the AC and it will go through a diode rectifier which will form the DC link of the inverter, and then this inverter switches from that DC link and produces a variable AC which drives the AC motor. So in an AC motor drive, or in an AC drive, we see that there are 2 stages of power conversion. First is the diode, or first is a rectifier stage, and the second is an inverter stage. And therefore, in many applications, the first stage, which is made up of these rectifiers, is done through diode bridge rectifiers. Okay, so diode bridge rectifiers actually find a lot of application in AC drives. The other application which is very important is EV chargers. As you may note that EV is getting very popular nowadays, and what we see is that the batteries inside these EVs need some form of a rectifier. Okay, because the batteries are DC, so it requires DC voltage and a DC current, whereas our grid is AC. Okay, so we need some form of a rectifier in between which can do this charging of the battery. So EV chargers is also one very important application of rectifiers. So there are other types of applications also. Now so these are like diode bridge rectifiers. Thyristor rectifiers are also used. Thyristor rectifiers are used in, say, nowadays it is getting less and less popular, but it is still very much in use in line commutated converters in HVDC applications. So there are two types of rectifiers basically that we will cover in this course, or in this first part of the course. In later part of the course we will talk in much more details about PWM rectifiers, but during this first module we will primarily concentrate on uncontrolled rectifiers, which are made up of diodes, and controlled rectifiers, which are made up of thyristors. Okay, uncontrolled rectifiers with diodes are simple because you just have to install the diodes, but the output voltage cannot be controlled, whereas in thyristor rectifiers, it can, by changing the firing angle, you can modify the DC output voltage. So one of the reasons why diode bridge rectifiers in particular have been in use for the last, say, 50 years is because it is low cost and the ease of implementation. It does not require any gate driver. It is very robust. It is cheap. So these are some of the great advantages of diode rectifiers, and that's why it has been popular for a long time. So here you can see some of the pictures which I have taken from Wikipedia, and these pictures show some of the diode bridge rectifiers. Of course, these are small rectifiers. There are many big ones available, and here you can see, for example, this is a diode bridge rectifier, and here this is a single phase diode bridge rectifier, and here you can see these are the two AC terminals. You can see here this is the AC signal given to this, and here is the plus DC and minus DC. Okay, so this is a rectifier, for example. So you can just use it as it is. Most likely this can be used in a through hole PCB mounted. So this is a through hole PCB mounted element, and you can put it in and use it in the circuit. Okay, so there are other types of rectifiers also. This is also one of the very popular types of rectifiers. And so these kind of rectifiers come in a variety of size and ratings, say few amperes to kiloampere, thousands of amperes of rating, and few volts to thousands of volts. Okay, and so and many various manufacturers, as you can see, Semicron, Infineon, and you should go through these, or there are even more. So these are manufacturers of these diode rectifiers, and you should go through their site to get a feel of what are the different types of products that they manufacture. Now, one of the things, before we go into the diode bridge rectifiers, one of the things is we should understand is the requirement of rectifier. This slide we will come back repeatedly in the course, because this is an important slide which says what do we expect actually from a AC to DC rectifier. What is the requirement? Okay, and here we see that there are actually several requirements from a rectifier, and not always necessarily all these requirements can be satisfied by a single converter. Okay, for example, the primary requirement, what do we want from the rectifier, is that first is that we should have a good output DC voltage. Okay, what do we mean by good? Good means less ripple. Okay, so we want a rectifier, we want a DC, we don't want any ripple, so we don't want something like this here. Okay, this is not we want. This we want a less ripple output DC voltage. So this is one of the requirements. Second is that the output DC voltage is adjustable. Okay, so which means that this voltage we can actually, so if I say V0 with respect to time, okay, this voltage should be adjustable, which means that as per the user demand, we can increase or decrease the output DC voltage. This is many times this is required actually. The third requirement is that input current taken from the grid. So if you think of the rectifier as a black box, here is your rectifier. Okay, And so suppose we take a single phase, so this side is AC and this side is DC. So the output side, we have said that the output DC voltage should be stable and less ripple and all, but the input current means the current taken from the AC side. Okay, this input current should be nice. What do you mean by nice? So there are quantitative measures for how nice is the input current waveform, which we term as total harmonic distortion and stuff like that. But basically we want this current to be sinusoidal. Okay, so we want this current here to be sinusoidal as much as possible. Okay, there are quantitative measures, but I am talking here qualitatively. So input current taken from the grid is sinusoidal. The fourth is that the bidirectional power flow. Now, bidirectional power flow, you may ask why bidirectional power flow is needed. In many cases, we use rectified. So normally, when we say the word rectified, energy is flowing this way. Okay, energy is always flowing from the AC side to the DC side. This is the conventional meaning or conventional terminology of a rectifier. However, under certain cases, what we can see is that the energy can also flow from the DC side to the AC side. Okay, in that case, this rectifier will no longer be called as rectifier and will call as converter. Okay, because then the energy is flowing from the DC to the AC side. Where do we find this kind of application? There are many places where we find these applications. For example, suppose let me take a different color. Suppose you have a motor drive here. Okay, suppose this is a motor drive here, and this motor drive is feeding to a load, and this is the DC link of the motor drive. Okay, under certain condition, this motor drive, suppose we are running a car through this one, not a car, suppose it is running, this motor drive is used in a railway traction. Okay, where we have the grid, AC grid here, this is the grid. Okay, and this is the motor drive for traction application. Okay, railway traction. And so under certain condition, we do regenerative braking. We want to save energy, okay, during braking of the traction motor. And when we do that braking, actually we can feed the energy, the kinetic energy of the whole system into the DC link. Okay, here is the DC link here. Okay, into the DC link, and then this converter, then this front side should feed the energy back into the grid. Okay, this is what we mean by the term when we say converted, because now the energy will flow backward. Okay, the energy should flow from the DC link into the grid. Only then we can actually save some part of the kinetic energy. We will give it back to the grid so that we do the energy saving. Okay, this is quite substantial actually. In many cases, we have found that in big traction locomotives, about 20 to 30% of the energy can be saved in this fashion. Okay, so we can actually feed energy back. Now, in that case, what happens is we will no longer call this as a rectifier. Okay, we will call this as a converter. Okay, so when the energy can flow in both the directions, we call it as a converter. Then it is called as a power converter. But when energy is flowing only from the AC to DC side, we can use the word rectifier. Okay, when energy is only flowing one way. It is good to have this bidirectional power flow. It is good to have, but of course it becomes more and more costly, because as you can understand here, that one of our requirements will always that this comes cheap. Okay, anything we build must come cheap. Okay, we cannot build a product which is so costly that it cannot come into the market. Okay, so we also want the rectifier to be small in size, because it should fit anywhere which we want to fit it. Okay, so that it shouldn't have a lot of size and weight and all those stuff, and should work for a wide variety of voltages and power. Okay, So you can feed the rectifier from few hundreds of volts to 1 kilovolt and few hundreds of amperes to thousands of amperes ideally. Okay, these are ideal requirements. And lastly, of course, all the time we say that we must have a good efficiency. Okay, why efficiency is important? Because efficiency is more important. Say, suppose there are two rectifiers, one is having 97% efficiency, another having 98% efficiency, for example. It is not that 1% is important. Okay, if you see the loss point of view, the 2%, there is 2% loss in one case and there is 3% loss in the other case. That loss percentage is substantial. Okay, that loss actually dictates how much is the temperature rise in the device and how much heat sink you have to provide, or whether you have to provide additional cooling like a fan or a water cooling or anything. So efficiency is not important simply because it is going from 97 to 98%, not that. Okay, it is not so important, but the losses are substantially going down from 3% to 2%. That is important. Okay, and that will dictate how much is your thermal management effort that you need to give. Okay, so therefore efficiency, having a good efficiency in a rectifier is always very nice. Now you can see here there are several requirements here which I have listed. Okay, and not all of them can be satisfied. Okay, for example, diode bridge rectifiers. So diode bridge rectifiers are very good in, so let me just use a different color. Diode bridge rectifiers are very good here. They are very cheap. Okay, and they are actually good when you use with a good output DC voltage. Okay, and it can actually come with a wide variety of voltages and power and all those stuff, but they are not good in terms of, so they cannot, so bidirectional power flow is not possible in a diode bridge rectifier. Input current is very bad with a diode bridge rectifier. Output DC voltage is not adjustable like this. Okay, so rectifiers, but it is very cheap. Okay, so this is very important. Okay, from if you want to commercialize, diode bridge rectifiers are very cheap, easily available. You don't have to worry much. You don't have to have a gate driver circuit, nothing. Okay, so it works nicely. Okay, but even then you will see where is the thyristor. So when you talk about thyristors, then you will see that, say, thyristors, output DC voltage will become adjustable with a thyristor. Okay, but input current is bad. Okay, bidirectional power flow is possible, but it causes some problem. So in this way we can say, so if you go to MOSFET based drive PWM rectifiers, then you will see that it has very good efficiency. Okay, MOSFET, silicon carbide MOSFETs have very good efficiency when it works as a PWM rectifier. Okay, so so therefore, as you can understand, one single converter cannot have all the good qualities. Okay, that is why we go to different types of converters, topologies, and different types of power devices. We'll see one or few of them. So we'll start with the most basic diode rectifier circuits. Okay, so this here is so as you can understand, this is the block diagram. Overall, this is the full wave or half wave or full wave rectifier, and this is the three-phase version. Okay, this is the three-phase version of the rectifier. We have an AC side here, we have a DC side there, and this is how the we will go through the three-phase sometime later. We'll start with the this full wave circuit here. So what is the circuit? It is the most basic. If you see, it is the simplest rectifier is just putting a diode. Okay, so the diode acts as a valve, and therefore it allows the current only in one direction. Okay, and so the diode is forward biased when the input voltage is positive. So only when this voltage is positive, the positive half cycle only, the diode will conduct. And some waveforms are shown here, and you can see here that if this is the input voltage, so this is the input voltage here, Vs is the input voltage, and the output voltage, that is the voltage across this load resistance, is something like this. Okay, it is the diode is conducting during the positive half and the diode is not conducting during the negative half, okay, because it is reverse biased, okay. And since the diode is forward biased, the input voltage, so if the diode is ideal, there is no drop across the diode, and so the output voltage is an exact replica of the input voltage, and so this will happen, okay. The output current is Vs by R, okay. What is the what is this waveform? This waveform is the voltage across the diode, okay. And what happens, so when the diode is conducting here. So if you see here, the diode is conducting here and the diode is blocking here, okay. So when the diode is conducting, the voltage across the diode is 0, okay. This we are assuming to be ideal diode. Of course, in practical diodes there will be a voltage, on state voltage drop, which is a slight voltage, maybe 1 volt or 1.5 volt, something like that. And this is the conducting part. But what happens, what is the blocking voltage? See, blocking means that when the diode is not conducting, how much voltage is coming across the terminals of the diode, basically anode cathode terminals. What is the voltage coming across? So of course, when the diode is not conducting, I can see that this point's voltage, so if this is a plus and minus, the maximum voltage that can come across the diode is nothing but this input voltage, which is this voltage here, okay. This is what will come across the diode, okay. So if this value is minus Vs, this voltage is minus Vs, so this same minus Vs voltage will come across the diode here. So this is the voltage rating of the diode, okay. This much it has to block, and this is the voltage rating of the diode, minimum rating that we have to provide. Of course, we will add a safety factor to it. So voltage rating of the diode is this much, okay. Minimum you have to put Vs in this case, okay. Anyway, what is the average output voltage? Why we are interested in the average output voltage? Because we are converting AC to DC, right? You can see here, this is DC, this is a DC quantity, okay. It is unidirectional, all the voltage is above the zero axis, okay. So this is a DC, and of course the average voltage is going to be somewhere here. This is the V0 average, okay. This is the V0 average, some voltage which is coming here. What is the value of this? Value of this can be readily found out by seeing that this voltage is this is 0, this is pi, and this is 2 pi, and so the voltage is Vm sin omega or Vs sin omega t. Sorry, there is Vs sin omega t dt here, okay. Vs sin omega t dt here, and therefore this voltage will be from 0 to pi, this voltage is there, but from pi to 2 pi the output voltage is 0, okay. So therefore if you integrate here, so basically you are integrating Vs integral Vs sin theta d theta, okay, and you are integrating from 0 to pi here, right. So you can easily integrate this one. This will be cos theta and pi to 0, and this will be 1 minus cos pi, which is 2. So here it is Vs cos theta, yeah, V1 minus cos pi. So therefore this will be 1 by 2 pi into Vs into 2 into Vs, so which will be Vs by pi, okay. So therefore this voltage will be coming across the output voltage, okay. So this is here, this value here is equal to Vs by pi, right. Now so this is the average voltage that we can get out of this half wave rectifier. Although very simple in structure and very simple to make this converter, okay, it is also a rectifier, but the problem is that we are not utilizing the negative half. So we are basically not utilizing this part of the waveform at all, and so therefore this is not a very good converter, very good rectifier. Although it may be very cheap and very easy to use, we are not usually utilizing the negative half of the AC cycle. So a better solution is to have a full wave or a bridge rectifier circuit. Okay, and we will get double the average output voltage, and we can see how this full wave rectifier works. So we see here that suppose we take this half, this is the first cycle, suppose we take this one, and we can see here that in the first half, okay, these two diodes, so in the first half or in the positive half, the input voltage is something like this here, okay, and so this current is flowing like this and going like this and coming like this and going like this, and this is how the circuit gets completed. So basically one pair of diode D1 and D4, so this one D1 and this D4, these two diodes are conducting now. When they are conducting, and if you assume that the diode voltage drop across the diode during conduction is 0, so these are ideal diodes, what we will see is that the output voltage is nothing but this voltage itself. Okay, so just hold on, so we will, okay, so this is the output voltage. Okay, here is the output voltage, and since it is a resistive load, output voltage, the output current will follow the output voltage as it is divided by R. So therefore this is the waveform of I0. Now what is the voltage across D1 and D4? Okay, so when the D1 and D4 is conducting, of course the voltage across it is 0, ideal diode. Okay, but what about the voltage across D2 and D3? How do we know that? So in order to find out, we see that this is the voltage. If you see this as the terminals here, when this diode is conducting, like D1 is conducting, so let me use a different color. When this diode is conducting, this plus point is immediately coming at this point here. Okay, so if we use that, so this is the plus point that is coming, because this is shorted and comes here. Okay, whereas this negative part is coming here. Okay, so which means that this diode here is blocking this voltage Vs. Okay, it is just blocking this voltage as it is going, so exactly, but it is now blocking. Okay, it is on the other side. The anode is more positive than the cathode is more positive than the anode. Okay, so therefore this voltage will come across the diode D2, and so this will determine why are we actually plotting this waveform of the other diode. The reason is we want to know how much this diode has to block. So this is the voltage rating of the diodes. Okay, so by which, so when we go to the market and try to buy a diode, we will say this is a 100-volt diode, or this is a 600-volt diode, or 1200-volt diode. So that 1200, what does it mean? It means that how much is the blocking voltage of the diode. That is how we choose a diode. Okay, so this voltage here, which we are saying minus Vs, so suppose this is a 230-volt system, so then this voltage will be 230 to root 2. Okay, typically in India we have 230-50 hertz system. So this is a 230 root 2, which is roughly comes out to be like 320 which roughly comes out to be like 325. कुछ गड़बड़ हो गया. Indian system, we have a 230 volt 50 hertz system, and so this peak value will come out to be 230 root 2, which is about 325 volt or something similar, close to that voltage. So this is the minimum voltage rating of the diode required. Of course, we will add some safety factor. We may choose some 1.5 times 50 safety factor. So this is the voltage across the, so D2 voltage we have seen here like this. Okay, and what is the current rating of the diode? So this current rating of the diode means how much is the current that is flowing through the diode. In this case, we understand that this is the peak current that is flowing through the diodes. Okay, so that must be at least the current rating of the diode. We will assume, of course, a safety factor. And what will happen in the negative cycle, and you can see this is the negative cycle of the AC input waveform, and we can see here that during the negative half cycle this terminals become positive, and therefore this diode and this diode becomes these two diodes become forward biased, and then a conduction happens, and this is the output voltage. Pretty simple. And so therefore the output voltage here is something like this, okay, which is we often call it as a rectified AC sine wave. Okay, so this is the output voltage that we get across the load. One thing is important is how does this transition, okay, happens. Okay, this is important. How does the transition happen? So for example, till this point D1 and D2 were conducting, and at this point this is the transition point, and then D2 and D3 D1 and D4 were conducting here. So till this point D1 and D4 were conducting, and at this point D2 and D3 starts to conduct. So how does this transition happens? So during this point, so let us concentrate here, okay, just at the point where the zero crossing is happening. So momentarily, okay, so the D1 and D4 were conducting, okay, during this point D1 and D4 is conducting, and we are actually trying to see what is exactly happening at that zero crossing. Okay, we want to zoom in and see what happens during this point. Momentarily for a moment you assume that D2 is also conducting, momentarily assume. Now at this point here, okay, just when the voltage is going towards the negative side, if D2 starts to conduct, okay, if D2 starts to conduct, what happens is, see this point's voltage here, this point's voltage is now going more and more positive, okay, the negative terminal of the AC, that is going more and more positive. So momentarily if you assume that D2 has started to conduct, what will happen is this point will come and hit here, okay. So because this diode is ideal, so this positive voltage will come and will be the voltage at this point, okay. So as soon as this happens, you can see here that this diode will now become reverse biased. So momentarily we assumed that both D1 and D2 started to conduct. Earlier D1 was conducting, and momentarily we assume that D2 has started to conduct. As soon as D2 starts to conduct, because now we are going towards the negative of the AC voltage, then therefore the D2, this voltage will come here and it will reverse bias this D1, and therefore D1 will stop conducting, okay, because we are assuming all ideal behavior of the diodes, and therefore this is how actually the current will commute from D1 D4 pair to D2 D3 pair, okay. This is how it happens. So the two diagonal, the current gets changed from one set of diodes to the other set of diodes through this process, okay, fine. And of course we have already seen what is the output voltage. So V0 is something like this. What is the average or the DC component in the output voltage? Of course, when you have this one, we only need to integrate from 0 to pi, okay. So we have integrated from 0 to pi, and we will divide by 1 by pi, because that we are going to integrate only from this point to this point, because the second part is a repetition of the first part. And so Vs sin omega t d omega t, and when you do this one, you will see that this is double to Vs by pi, which is double than the half wave rectifier, okay. What is the RMS voltage? What is the RMS voltage? So what is the RMS voltage of this? This is very easy to find out, because it can be found out just by inspection. This RMS voltage is Vs by root 2, okay. We don't have to calculate because this is coming directly from this voltage, okay, and this has an RMS of Vs by root 2, and so this has also the same RMS of Vs by root 2, because this negative part is same as the positive part here, okay. So RMS voltage is Vs by root 2. Now we will take an example here, okay, and see why is this RMS quantity important, okay. And so So a DC load, okay, so there is a diode bridge rectifier. So basically a DC load is with a resistance of 20 ohm is used for heating, for example a geyser. Okay, so we have AC system here, AC coming here, so there is a diode bridge rectifier and there is a resistive load which is nothing but a geyser. Okay, yeah, this is a very crude example, but anyway, you can see here, and fed from a 230 volt single phase supply and a bridge rectifier. Okay, so what is the power consumed by the load? Okay, so power consumed, what is the power consumed by the load? So instantaneous power is V into I. Okay, instantaneous, so power, average power that is flowing is, we know that this is like this. Okay, so instantaneous power is V into I across the load over dt period, and this is the, therefore, the average power. Okay, now we have to find out what are these values. So this is the voltage across the voltage here, the voltage across this one is this voltage here. Okay, this is the output voltage, which is Vs sine omega t, right? What is the current? The current is Vs by R sine omega t. This is the value of the current, and we need to only integrate from 0 to pi, because the from pi to pi is a pi to 2 pi is same as a repetition. So we just integrate from 0 to pi and divide by the time period pi. Okay, so this is how it will. So when you put these values, you will get this sine square omega t, which will be 1 upon 2 1 minus cos omega t. And when you do this integration, what you find is basically this value. Okay, Va square by 2R, which is nothing but load RMS square by R. Okay, and load RMS square is nothing but the 230 squared by 2. Okay, Va squared by 2, right, same as the input voltage, and so this value comes out. So here the AC input voltage, okay, it has this, the out load RMS value is having the same RMS value, the load voltage has the same RMS value as the AC input voltage. Okay, so this is the load RMS. Okay, we will come to this example sometime later. Now comes the RL load. Okay, where do we use RL load? Where from this L came? So basically in many of the applications this is part of a motor load. Okay, usually say in earlier times we had DC motors, as I have told you, and DC motors have very big windings. Okay, and where the inductance is substantially high. Okay, so we will either use RL or RLE load, yeah, motor load. But if I assume, suppose, let us understand what change it will happen, what change will happen when we use the RL load. Okay, now and then we will see what is the motor load. So when we have this RL load, what happens is we observe something very peculiar, and the peculiar thing that we'll observe is that we will see that the output voltage becomes negative, okay, but the current remains positive. This is something very peculiar, that thing happens in case of an RL load. Okay, so to start the analysis, we say that within RL load the current will always not follow the voltage. In a resistive load, V and I are related by the proportionality factor R, but in this case Vs minus Vd, so we can just write the KVL, Vs minus Vd, Vd being the drop across the diode, is R plus L di dt. And so the diode will conduct, okay, as long as this voltage Vd is positive. Okay, so here we see that Vd, this Vd voltage is Vs minus Ris minus L di dt if it is greater than 0. Okay, as long as it is greater than 0, then the diode will go on conducting. Okay, the diode will be forward biased and it will go on conducting. Now see what happens. Suppose we have started this voltage. Okay, so this is where the voltage, this is the input voltage waveform, and see what happens with the current here. Okay, this is the current which is flowing. So this is the current Is and I0. This is the current I0. Okay, see what happens is during the initial period, say this is the 0 to T1 period. So what is happening? The current is rising, the voltage is rising, so the current is also rising. Okay, and so the diode is conducting positive current. So the diode is conducting, current is building up. So here the current is building up, and the inductor, the half Li square energy in the inductor, that is also increasing. The inductor is storing more and more energy. The VR, the voltage across this resistance, is nothing but a replica of the current. So this is I times R. Okay, the voltage across the inductor is L di dt, which is dependent on the slope of this current, and so it will be something like this. Okay, we'll come to this. Now the voltage across the total voltage V0 here, which is plotted here, this is the total voltage V0, and it will also follow this input voltage. Okay, because the diode is ideal, it is going on following the input voltage. Now so because if I assume that Vd equal to 0, okay, then Vs minus Ris is L di dt. Okay, we have assumed Vd to be 0, and we have seen that this is the equation. Okay, at the bottom this is the equation that we are following. So Vs minus Rs equal to L di dt. Now after t equal to 4, t by 4 means after quarter cycle, that is pi by 2, what happens is the voltage starts to fall. Okay, Vs starts to fall. Then now, because now the voltage Vs value, this driving force here is now going lesser and lesser in magnitude, right? At some point what will happen is Vs minus Ris is becoming going to be less than 0. So this left hand side will become less than 0 because Vs is falling. Okay, so Vs has started to fall, and at some point the current has also started to fall, and therefore Vs minus Rs will come out to be less than 0. Okay, and then what happens, the earlier this L di dt was greater than 0, this factor was greater than 0, and now it will become less than 0. When L di dt was greater than 0, the current was rising. When L di dt has started to fall, then the current will start to fall. Okay, okay, so when the current starts to fall, which means the slope of the current has changed. Okay, the slope of the current here has changed, therefore this L di dt will become negative. Okay, the absolute magnitude of that L di dt will become negative, and therefore what will happen is this equation, so the voltage across the diode will become Vs minus Ris plus L di dt. Okay, plus, this is important here. Okay, because the current has now, the slope of the current has changed. Okay, so it is becoming plus L di dt. This plus L di dt, what will happen is this plus L di dt will counter this Vs minus Ris. Okay, so even if the source voltage has become negative, so Vs can go negative, but the overall term Vs minus Ri plus L di dt, that may remain positive. Okay, which is happening here. You can see here that okay, after this point Vs has gone negative. You can see here what is happening. Vs has gone negative, but the current is still positive. Okay, so this voltage here is negative here. Okay, but the current is positive. The current is positive here. Why? Because this Vs minus Ri plus L di dt, that term is still positive, and that since that term is positive, Vd remains positive. The voltage across the diode, this voltage here is still positive, and it will go on driving the current till the point where this Vd becomes negative, and this will come at this point here. Then the diode stops conducting, which will happen when the current becomes 0 actually. Okay, so this is a peculiar condition which I was explaining, that during this time here this is a positive current, okay, and a negative voltage which is coming across the load, Okay, this condition is because of this inductor, and it's the behavior of the inductor. So basically what is happening is that the inductor is storing the energy at some initial point. Okay, when the current was rising, the inductor was storing the energy. So you can see here the VL, inductor is storing the energy, and during the other part, when the current was falling, then the inductor was releasing the energy. Okay, so the inductor was releasing this energy, and so we can say that the inductor stores energy from 0 to T1 and returns it back during T1 to T2 period. Okay, so we can say that this so as long as the inductor stores the energy, it will go on driving the current, and therefore the diode will remain forward biased. Okay, when the total energy of the inductor is exhausted, then the current will go to 0, and then we will have the conduction stopped. So the we can also say that the integral of this voltage here is the must be 0. Okay, which means plus area and minus area here, these two must be equal. Okay, of course we get less output voltage than the R load case, because you can see here the output voltage has become negative here. So the average output voltage will go down because I am now allowing a certain negative voltage across the load. Okay, so this is going to happen here. Achha, just hold on. So now we see, so we understood that what is this RL load and how does it work, okay, with a very simple single diode. But normally this happens with an RL load or RLE load like this with a full bridge circuit. Okay, this is more practical, and this is nothing, this here is nothing but a DC motor. Okay, so we can as well write it like this. This is the DC motor which is being fed from this from this AC supply. Okay, and we can assume that this RLE load as the equivalent circuit of the DC motor. Okay, so in the past this technology was popular in trams and single phase traction systems where DC motors were used very much, but nowadays DC motors are not so popular. So one of the things that we can see is, going back to the slide, is that this waveform of the current, okay, what will happen if we go on increasing the value of L? Okay, if we go on increasing the value of L, what will happen is this waveform will kind of like, it will extend, okay, like this. And if we further go on increasing the value of L, what will happen is sometimes the current will not even touch 0. Okay, it will not touch 0. Okay, because you are increasing the value of L. And if you have a very large value of L, which is the case of a DC motor, then what will happen is this current will become like a constant here. Okay, so this is the from the discontinuous conduction of that RL load or RLE load, we get not only a continuous conduction but a continuous conduction with ripple free output current. Okay, so it becomes like a very steep current here. So then this circuit we can replace with a constant current load here. Okay, this is typically for a DC motor. It basically means all the time constants is a relative time constants. Okay, a DC motor has, so if the R and L values of the windings are so high that the time constant can be several seconds, and this time constant here, this AC circuit has, you can see here, this is like, if you see here, this is 20 millisecond in a 50 Hertz system. Okay, so this has a very small time constant, 20 millisecond as compared to seconds for a DC motor, okay, winding. So during the time in which the AC waveform is completing one cycle, the DC current for the motor, okay, it hardly changes, right? So because it has a very large time constant, so therefore we can assume that this current is kind of like flat and it doesn't change within the small time period in which the AC wave is changing. So therefore in this case what we can do is we can assume the circuit to be like this one. Okay, we have a AC input and we have these four diodes present, and the constant current load can be assumed at the DC side. Okay, so the large value of inductance resists any change of current through it, hence the current appears constant. So what will happen now here is that for half of the cycle these two diodes will conduct, and for another half of the cycle these two diodes D2 and D3 will conduct here. Okay, fine. Yeah, so this is some of the waveforms. As you can see here, this is the current I0. Okay, and in the positive half cycle diodes D1 and D4 are forward biased. So when the diodes D1 and D4 are forward biased, then we get this voltage across the load, and the current, this current here, the source current is same as the load current during that point of time. So the source current is something like this, it will follow like this, okay, which is nothing but the load current here. Okay, the source current follows the load current here, and in the negative half what will happen is that this is the negative half of the cycle, and the current still remains the same, the I0 current, this current remains the same here, load current, but now the two other diodes are conducting, and therefore this is the path which is given by the dotted line, and so this current is something like this here. Okay, the source current here it goes like this. Okay, the source current is AC, right? It has a positive part and a negative part, so that is fine. However, the source current shape is the source current shape becomes a square wave. This is a problem. Okay, it is highly non-sinusoidal. The source current, if you can see here, this source current, instead of being a sine wave, becomes a non-sinusoidal wave. It's a square wave. So this will cause a lot of source current distortion, okay, which results in poor power factor, and the grid which is supplying this kind of a source current will not allow it, and even if it allows it, it will have a lot of penalty which will be associated with this kind of a source current which is drawn from the grid. So remember, the grid is here and you are supposed to draw a sinusoidal current from the grid, but now you are drawing a square wave current from the grid, and the grid does not like it. Okay, it has other problems which we will discuss. Okay, power factor, distortion factor, harmonic distortion, etc. Okay, so we will just take an example here. Okay, suppose there is a constant current load of 10 ampere. Suppose this is part of a DC motor. Okay, so it's drawing a constant current load of 10 ampere. It fed from a 230 volt single phase supply and a bridge rectifier. Okay, what is the power consumed by the load? Okay, so again, what is the definition of average power? Power average is 1 by T integral to Pt dt. Okay, this is the definition of power. Now in this case, okay, what is V and what is I? V is this waveform here, okay, which is the rectified sine wave. Okay, so we can only integrate from 0 to pi, right, and we will have a time period of pi, and then this is the V, okay, Vs sine omega t. But I, what is I? Now I is here in this case, because it's a DC motor load, I is constant, right? I equal to I load, I is constant, so I load is here, which is a constant, and d omega t, right? So when you put these things, what you get here is that when you do the integration, you see that it is 2 Vs by pi into I load. Okay, what does it mean? This means average load power into I load. Okay, average load voltage times I load. Okay, now remember from the previous example, in the previous example which was this one, which was this one. In this example, this output voltage was RMS quantity, because it was a resistive load. Okay, now we are talking not a resistive load, we are talking a DC motor load, okay, which is nothing but an RLE circuit, E the back EMF of the machine. Okay, so here E is the average voltage, so the power which is getting transferred to this motor is the average voltage times average current. Okay, so this is the average current, okay, average current, and this is the average voltage. This is not RMS voltage. Okay, so average voltage into average current, and therefore this power is 2070 watt. Okay, so you should compare this result. Okay, so in the geyser case, there was the full load was a resistive load, and the RMS value of that voltage we had taken. But when we had an average, when we had a DC motor which had a back EMF E, or suppose this can also be used for a battery charging, then we will say battery voltage times average battery voltage times the current that is flowing. So average voltage into average current. Okay, and so with this thing we are basically covering the basic introduction of single phase diode bridge rectifier, and next we will take up the three phase diode bridge rectifier and probably thyristor rectifier. So now we will talk a little bit about the effect of source inductance, okay, in different types of rectifiers. We will just touch this subject briefly. This effect was, I mean, this effect has been studied very thoroughly, and basically when you see these kind of diode rectifiers or even thyristor rectifiers, okay, we have this say diode or thyristor rectifiers, and we have a load here. Usually this is the grid, whether it is equally applicable to three phase or single phase. I am taking a single phase one here, right? Usually this is basically supplied through a transformer. Okay, through a transformer. The transformer gives isolation, voltage step down, and this isolation is required from safety point of view for the working personnel. So this transformer actually, of course, this isolation and safety requirement is one reason why this is used, but it has some adverse effect on the operation of the converter, and this is basically termed as the effect of the source inductance. So this transformer, if you see, this transformer is basically nothing but a RL circuit. If you take a simplified representation of this transformer, is nothing but this leakage, the primary and secondary leakages can be represented by this RL circuit, which if the R is very small, this can also be kind of like represented by this like this. So this is what is shown here. Okay, this the source inductance. Now, what is the purpose of or what is the effect of this source inductance? Okay, the source inductance plays a role during the commutation of the diode bridge rectifier or the thyristor rectifier. So basically the effect is that we will lose some of the voltages. Okay, so we will lose some of the voltages from this whatever voltage we apply here from the grid, some part, a fraction, very small, maybe 2, 3, less than 3, 1 or 2%. So 1 to 2% of that voltage may be lost here. Okay, because there is of course a drop of the voltage, so we will lose some of the voltages which will be available. So earlier when thyristor rectifiers were predominantly used, then this was very detailed, this was studied in details, because this used to affect the commutation of the thyristors, and we used to see notches in the output voltage because of this thing. But since thyristor rectifiers have become not so popular now and almost like diode bridge rectifiers, so we are going to study this in very brief in the next 10 minutes, just to see what is the effect of this source inductance. Okay, so in order to understand the effect of the source inductance, we will see a very simple circuit. Okay, this circuit is basically a half wave rectifier with the two diodes. You can see here, this is the source. Okay, there are these two diodes, and this is the source inductance. Okay, so and this is feeding to this constant current load. So this is the source voltage waveform, and we will see what are these waveforms coming up, right? So what see, let us assume that we are we are focusing at omega t equal to 0, right? This at this point omega t equal to 0, right? So before this omega t equal to 0, let us assume that this diode was already conducting. Okay, this diode was taking up the current, and at omega t equal to 0, D1 is getting forward biased, right? Because after omega t equal to 0, from this point onwards, D1 is getting forward biased, while D2 was already conducting, right? Now, because of this presence of this source inductance, what happens is the current through D1 cannot immediately rise, okay, and it will cannot become I0, because this is the total load current, I0 instantaneously because of the inductor, because the inductor will always have L di dt. Okay, it will not allow the current to rise immediately to I0. So what will happen, because this is a constant current source right here at this point, so therefore the total I0 must be equal to this current plus this current which is coming. Okay, so these two currents must be equal to I0, right? But since this source current Is, okay, is not equal to I0, therefore this diode will continue to conduct, D2 will continue to conduct as long as I0 is 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 equal to I0. Okay, so therefore since this D2 is conducting, so let us see this transition where the commutation is happening. So during this transition, what will happen is this diode is conducting, so this is shorted. So therefore this point's potential and this point's potential is same. So if the diode drop is neglected, then which means that the voltage which comes across the inductor, this voltage is equal to Vs during this point of time, because this is the circuit here. Okay, this point is connected here, so which means Vs voltage will come across Ls. So this voltage is shown here, VL. VL is the voltage across the inductor, which is equal to Vs during this point of time, right? Now since D2 is conducting, D2 is still conducting, right? So therefore if D2 is conducting, the output voltage cannot be the output voltage must be 0, okay, right? Because D2 is conducting. So therefore now the condition is that Vs is equal to L di dt, since D2 is conducting, and Vs is equal to VL. Okay, so during this point, so slowly the current will start to rise, because this is where the L di dt factor will come in and the current will rise. Okay, so D1 current will rise and D2 current will of course fall, because the sum of the two currents must be equal to the I0. Now at some point which is equal to omega t equal to mu, okay, then this I0 Is, this will become equal to I0. Okay, at that point the D2 will stop conducting, okay, and the entire current will be now taken up by D1. Okay, then at this point D2 will get open circuit and it will stop conducting, and the entire I0 current will now, this current here will now flow through D1. Okay, so D2 will stop conducting at omega t equal to mu. This point we are at mu, open circuit, and L di dt will become equal to 0. So what is the effect of this one is that we lost some output voltage. You can see here this output voltage we have lost, because after this only the output voltage starts to appear. The input voltage starts to appear at the output, because till this point here D2 was conducting, so we were getting 0 voltage. Only when D2 stopped conducting, we started to get the input voltage being applied on the output side. So we lost some output voltage, and we can actually find out how much we lost. Okay, and this is basically, you can see here, this is the end result. V0 is Vs by pi. Okay, this is what we had obtained if there was no source inductance, if Ls was 0. But now we are not going to get the full voltage, rather we will get 1 minus this part, 1 minus, so we will get a fraction of that input voltage. 1 minus this much of the voltage we will lose. Okay, so this is generally very small, maybe we get about 97-98% of the voltage, but we lose definitely 1-2% voltage we can lose. Okay, so this is the output voltage we will get. So you can find out how much we are losing this voltage, and that you can do by doing some of the mathematics. So for example, the amount of the voltage lost due to the source inductance, which we term as A mu, this is basically can be obtained by observing this one. So this is the area, so this is the A mu. Okay, this we are going to lose this voltage. So this is basically 0 to mu Vs sine omega t d of omega t, right? And we are going to integrate from 0 to mu. This point is here, the mu is given here. Okay, so so during the commutation period, okay, Vs is equal to L di dt, that is Vs sine omega t is L s dis, or we can substitute this Vs sine omega t by omega Ls dis. So if you put this back into this equation here, okay, we can get that this is A mu is equal to omega Ls I0, right? So that is how this we got this omega Ls I0 here, right? So therefore we have actually the output voltage is reduced by this factor here. So this is also applicable not only for the half bridge rectifier but also for the full bridge. So here you can see the full bridge, but here in this case also you can see the output voltage is, see, this is the 0 part here, here is the 0 part. Okay, and then we have the output voltage and we lose this voltage and the current goes like this. Okay, so in this case the output voltage is 2 Vs by pi. This is what we had seen earlier. This we will obtain when you have an ideal rectifier, but now we will lose a little bit of voltage here. Okay, so this so this is a small portion of the voltage that we lose, and this amount of voltage we have to anyway, this is a penalty that we have to do because we have to use a transformer in the at the input. So the transformer has a loss, so that is there, the transformer has a series loss, and as well as the output voltage will have another loss. So this is the total voltage loss that we have to encounter. Okay, and this voltage is not very much, and probably what is done here is that the transformer turns ratio is slightly changed so as to increase, so that as to compensate whatever is the lost voltage. Okay, whatever we lose the voltage, we compensate by slightly increasing the turns ratio. We get a slightly more voltage so that this drop is all taken care of. Of course, you need a transformer. You cannot get rid of the transformer because it is very important, because from the safety point of view, the transformer gives you galvanic isolation so that the output ground and the input ground are completely separated. There is no path. So even if there is an output short circuit, the current will not flow. So that is the main reason why we use these transformers, for safety reasons. So we have to use it, but we also understand that the transformer has certain drawbacks, one of them being that we lose a little bit of voltage. So it's not a very big voltage and we can take care of it.